morning. Welcome to the course on analytics, in which we are trying to study predictive, descriptive and prescriptive analytics. So, I am Dr. Amandeep Singh. I will take this topic sampling here. So, better to call it sampling techniques. So, the flow would go like this. We will discuss about some definitions or terms which are used in sampling. The introduction to sampling, what is sampling, then we will discuss various types of sampling, then also we will discuss the errors in sampling. Then I will try to give some general tips for sampling type selection. So, first a few definitions. Population and sampling. Population consists of the set of all measurements in which the investigator interested here. For instance, if I am interested to study the number of students who are interested in doing engineering in the city Kanpur. So, my population is all the students in the city Kanpur who are in non-medical stream, that is my whole population. Sample is a subset measurement selected from the population. To do this study, I cannot reach all the students. There would be about more than 1 lakh students in there. So, I will select some number of students. Some students, maybe I might divide it into demographic regions, or I might divide into the kinds of the schools they study, the status of the schools. So, that is kind of sampling. I am trying to select a small number from a big universe. That big universe is population. The small number is sample. So, the population is generally denoted by capital N, sample is denoted by small n. Now, sampling from the population is often done randomly, such that every possible sample of n elements will have an equal chance of being selected. That is called simple random sampling. A sample selected in this way, in the simple random way, is a simple random sample or just a random sample. So, example here may be, if I want to test the students of a complete school having about 2000 students, 2000 is my population, and then if I test a smaller group of students from maybe 30 to 50 students. So, this is my small n. Small n by capital N is known as sampling ratio. Sometimes it is also mentioned in the percentage. For instance, if it is in this case 50 by 2000 into 100, this is equal to 2.5%. So, this is an illustration that explains we have a target population, a sample is selected here. In this case, this is not simple random sampling, because if you see the students or the subjects here are distributed evenly. He has just selected one cluster, one group directly, but had he selected one from this side, one from here, one from here, one from here, one from here, I might call it simple random sampling here. We will see this thing in the forthcoming slides here. Then sampling can be simple random sampling with replacement, simple random sampling without replacement. So, with replacement implies I am selecting out of the 2000 students which were of my interest, this population is of my interest, I select 50 students, and when I work on one sample, that is sample is number from 1 to 50, 1, 2, 3, so on up to 50. I work on this sample first and then I replace this sample in my population again. Again out of 2000 I will select second number. Then after working on this I will put that in my population. Again I will select the third. This is with replacement. Without replacement is if I have worked, if I have taken the information from sample 1, this is taken out. In without replacement type, the information or sample is not replaced or put back in the population. In that case, if I have worked on the sample number 1, I have taken the information from sample number 1, I would not replace that sample in the population. Out of the remaining 2000 minus 1 samples, 2000 minus 1 elements, I will select sample number 2. This is called without replacement. So, this is a general representation here. If x has a distribution such that expected value of x is mu x, expected value is generally mean, and variance of x is sigma square x, this is variance. This is for population. Then expected value of xi would also be mu x and variance of xi would also be sigma square x, that is the sample behavior would be same as that of the population in case of random sampling we are talking. So, what are estimators and their properties? Estimator, any statistic or a random function which is used to estimate the population parameter is known as a statistic. So, in this case, this mu and sigma square are my statistics. So, let us recall something about the probability distributions. We had these estimators in discrete distributions. We had uniform distribution, then binomial distribution. In uniform distribution, we have the smallest and largest value. In binomial distribution, I have n and probability of success, and another discrete distribution is Poisson distribution, in which I have lambda as arrival rate. So, in this case, here A cap is equal to minimum value of x1, x2, so on up to xn, and B cap is maximum of x1, x2, so on up to xn. For instance, if I say marks of the students in the class are uniformly distributed. So, the minimum marks of the sample that is selected, for example, if I talk about these 2000 students and if I am looking for the marks out of the 50 students which are of my interest, the sample size. So, out of 50 students, the minimum marks would be A cap here for the sample and the maximum marks would be B cap here. So, here n is equal to 50 in this example. In binomial distribution, the p cap probability of success is the number that is favoring over total sample size. So, Dr. Deepu Philip have already discussed the distributions, probability distributions. So, I am just trying to recall that and giving an overview here. In this case, this lambda cap is same as average of the n samples. Then we have continuous distributions. So, before that I like to show you, this is discrete distribution, this is continuous distribution. Continuous distribution is like weight can vary, continuous, it can take any numbers. It is actually the ratio or interval scale, ratio or interval scale. So, this is discrete distribution, it is not connected, this one is continuous, and we will see that if the sample size is too high, in case of when I see the plots, if the sample size is too high, the histogram plots are like this in normal distribution. If I am having very large sample size, then this discrete distribution tends to become a continuous or behaves like a continuous distribution in this case. So, these are histograms which are separate, but we can draw a line that join these and we can call this as a normal continuous distribution, provided that these numbers 1, 2, 3, 4 are more than 30. So, this is in general. Continuous distribution, we have again normal distribution in which we have two statistics mu and sigma square, the mean and variance. Here mu cap, that is for sample, is equal to average of the sample, and if in normal distribution mu is known, then this variance is equal to 1 by n summation I varies from 1 to n xi minus mu square. If variance is unknown, these degrees of freedom reduces, this degree of freedom becomes 1 by n minus 1, and the other relation remains same. This is xi. This is the third case when a normal distribution has mean mu, variance sigma square, and if mu is unknown. So, this will be more clarified when we will see, when we will apply various kinds of tests, various kinds of when we will do analysis of variance, we will apply t test, we will do regression and similar kind of mechanisms. When we will learn, we will see that if the population mean is known, the degrees of freedom is n minus 1 and the variance is calculated by this relation. If population mean, remember mu is equal to population mean. If population mean is known, then this is the relation. Also another distribution is estimated. Then theta cap is equal to average of sample. So, I need to mention here that to select the distribution, it needs a detailed knowledge of how distributions behave. We actually see the data that is given for the sample or for the population. We plot the data, we try to fit the distributions here, and whichever distribution is the closest fit, we select that. We see that okay, this is the distribution fit, the coefficient of determination is the closeness to the distribution, that is coefficient of determination is very high for this distribution and it is very close to the sample. So, that we will practice when we will go to the R sessions, when we will see the R codes for this one. Next is sample size. So, we can raise the following questions while sampling, that how many observations. Now, second thing I can ask is bigger always better? Is bigger always better? As we are testing the sample and we will see whatever the behavior of sample is would reflect the behavior of population, and if sample is not selected properly, not a correct sample is selected, those can lead to errors. If from a lot, from a population, from a good population, bad sample is selected, from a group of intelligent students, only weak students are selected as a sample in case, and because of those weak students, the whole group of good students can be rejected. And in the other way, from a group of weak students, if intelligent student or intelligent a good sample is selected from a weak population, that whole weak population can be selected. So, when a good lot is rejected, that is the producer's error. When a bad lot is selected, that is the consumer error. For instance, if I say in the manufacturing, if we are manufacturing this pen, okay, out of the 1000 pens which are manufactured, I select a sample of 50 pens and the whole lot was good, but these 50 pens didn't behave well and I have rejected the whole lot. Who is at loss? The producer. And the other case can be if the whole lot is not good and the 50 pens which I have selected from 1000 population size is good, that has behaved well, the whole lot is selected. Selected, that means that would be sold to the consumers. Then who is at the loss? Consumers. So, this error of selection a bad or this error of selecting a bad lot is known as consumer error. We will see when we will plot the operation characteristic curve, the acceptance sampling. So, is big always better? It is the question. So, are the bigger studies always better? Then how many households, villages, if we are trying to do a study, a kind of a survey, how many household, which villages, blocks should I study when I do research on? How do I justify that to the donors or head of institution? How do we justify? Because sampling has cost associated with it. Sampling cost. If it is a kind of a destructive testing, for example, if I want to test the strength of this pen body, I need to apply some mechanical force here, I need to break this thing. So, these 50 samples would be destructed. So, there is a cost associated with that. All these 50 body or the pipes or the outer coverings would be wasted. So, sampling cost is associated, and in surveys or in market studies or in surveys also the cost is there. For each sample the researcher has to contact the respondent, he has to give him a questionnaire, then get it back, the time is consumed, the resources are consumed, and the cost is also there. So better to put here sampling cost and resources. So these are the key to limit the sample size. So increased or big sample size, large sample size has only a few advantages that I list here. Large sample size reduces sampling error. But it has many disadvantages, that is the non-sampling error is also there. The cost of data collection is high, that is money, time, resources are, one is cost, I put it here again, then time, then human resources, then I have here is data processing. So the question comes, what is the optimum size? What is the optimum size of the sample? So let us try to elaborate this further. Bigger is not necessarily better. Sampling errors are there. So what is optimum size? To work on this, I like to mention a few non-sampling errors. Non-sampling errors are the errors which do not have any probability, which do not have any calculation involved in that, but those do exist. For instance, the non-sampling error may be the failure to measure some units. Then maybe error in measurement. This can be the observer error, the one who is doing the study, or maybe the instrument error. Sometime the environment error as well. So sometimes in surveys there is non-response bias. People do not respond. Then sometimes the observer is maybe careless, or maybe data entry error, or sometimes misrepresentation of the facts, and some other errors like telescoping, reference period, etc. So these are non-sampling errors which have no probability or distribution or calculation. But the thing is that these do exist. So this is an illustration which is trying to explain the kinds of non-sampling error. So it can be due to the instrument, due to the respondent, and due to the enumerator or processor. So instrument, the definition and specification of instrument can be wrong, or defective questionnaire in case of survey, defective measurement tools. Sometimes the tools measurement, we sometimes use a questionnaire as a tool which is not easy for the respondent to understand. So sometimes the respondent has a strategic bias. He under or over reporting also happens, or non-response occurs, or sometimes I think very casually about the study and do not respond seriously. So these are respondent errors. The enumerator errors, the lack of training, if training of the that is the researcher is not very well conversant with all the ways, all the ups and downs those come during the practical survey. So poor coding and editing of questionnaire, getting the missing data, data cleaning, all that doesn't happen very good. Mistaken data entry, programming errors. So these are non-sampling errors which comes into play. So because of these errors, what should be the sample size? So I like to put that in a diagram here. We have errors here and we have sample size. So as we increase the sample size, the sampling error decreases. This is the sampling error. That is when the sample size is increasing. If I say this is my population, this is the total population, the sample size is increasing and it will be 0 at this case. It will touch 0 at this case if the whole, that is census study is done. Census is all the population, all the elements I will put. It is the complete population. Census study, second is sampling study. So the non-sampling error, because of the high sample size, so these errors could come into play. Instrument, respondent, researcher, it is increasing here. This is non-sampling error. So what to do? The best strategy here could be select this point. At this point, this is actually the total error, the blue line. Total error is the sum of sampling and non-sampling error, and this is the point where total error is minimum. I will also try to prove this statistically further, that the sample size or the sampling error behaves like this. So let me say if the population is way far from this and this is the sample size, this is sampling error. You see this error was this high at the beginning. So in the later stage the error is reducing. The error is reducing. At this stage the error is this much. So at this stage the error is already very less. After this, the gain, this much of gain, that is the reduction in error is too small. Is too small. Even if I go here, if I suppose this was, if I put a scale here, or let me put it 100, 200. So if I put a scale here like 100, 200, 300, 400 and so on, if I increase my number of respondents from 300 to 400, the gain would be about 2%. But if I increase my number of respondents from 100 to 300, this gain might be about if I say this is 100%, this is 100%, this gain might be about 40%. So, it is not recommended to have very large sample size. So, even if the population is whole country or whole city, lakhs of people are there, a sample size between 300 and 400 is a good number to work on. We will see how statistically this is true. So, next comes the statistical uncertainty. So, if this is standard error, sigma by under root n is the standard error of mean. This is the deviation, standard deviation of an average is obtained by dividing the original standard deviation with square root of the number of data values of n. Then at, let me say, at 95% confidence level, at 95% confidence level, the standard error is 1.96. Here 1.96 is the normal deviate here, 1.96 into the standard error. So, we can say x bar plus minus 1.96 sigma by under root n is our 95% confidence level. So, this value is my statistical uncertainty. The standard error here is for a finite population, the standard error is sigma by under root n into 1 minus n by n. Here capital N is a finite number, and that is the number of individuals in the population, and we know small n by big N. This n by n, as I said before, this is sampling fraction. So, the formula for the confidence interval can be modified in a way: x bar plus minus 1.96 sigma by under root n into 1 minus n by n. When the sample is very small, that is n by n tends to 0, this implies the relation under square root, that is 1 by n by small n by capital N tends to 1, then this relation x bar plus minus 1 minus 96 sigma by under root n stands true. We will see the practical significance of the statistical uncertainty when we will do the R code for that. I will show you the plots that how statistical uncertainty is important in determining the sample size and the kind of sampling strategy we should use. So, what is this statistical uncertainty? I would like to put this illustration here again. This is actually the statistical uncertainty which we call as sampling error. So, if I say this is 0, maximum it could be 1, the uncertainty. If I say this is about 0.4, 1, 2, 3, 0.1, 0.2, 0.3. So if the sample size is 100, 200, 300 and 400 and so on. So this is statistical uncertainty. The general formula for statistical uncertainty that is denoted by U is 1.96 under root P into 1 minus P by N. This is here the P is probability of success. So we can see this is maximum when P is equal to 0.5, and this is the chart for a sample size N and P is equal to 0.5. Here it is seen that the size between 300 and 400 is a good number. So big sample size does not mean we will have very less error. So the uncertainty is this much here at about 350. So this elaborates what I said, that even for very big studies the sample size of 300 to 400 is a good number. So this was about the sampling error. This was all about the sampling error. We are actually working on this sample size. Sample size. What should be the sample size? We are working on this thing. So for non-sampling error, there is no formula available. The decisions to reduce them are based on the past learning. Or experience. So that depends upon the nature of questions. Then for the researcher or the investigator, his background, that is the amount of knowledge he has about the study, then his training, then the commitments that he makes. Also, because there would be always some ups and downs, there would be always something different in the actual performance than the scheduled. So back checks are to be made. Back checks, or I could call it supervision or monitoring. This study is important. So what do you do here? Take feedback, or I would put record feedback and take corrective action. Then during coding or during analysis of data, the quality is to be maintained. Quality during coding, analysis, selecting respondents, etc. So no wonder there is very little discussion about non-sampling errors in the sampling theory. In our R platform, there would be no discussion about the non-sampling errors, but these contribute, these have a big role on the quality of the study, on the kinds of the results we obtain. So in this lecture, I discussed about the terminology in the sampling, the population, sample, sample size, discrete and continuous distribution. Then sample size depends upon the sampling error, non-sampling error. How are these interrelated? All these things we have seen. In the second part of this lecture, I'd like to discuss the types of sampling, the sampling strategies. So I'll take a break here. So let us meet in the next lecture. Thank you.